In this lecture, we're going to begin our study of second-order differential equations. So recall that second order means that the second derivative is going to appear in our differential equation. And we're actually just going to restrict our focus to linear second-order differential equations. And one reason for that is they frequently come up in practice. But I guess another reason is that if we have a nonlinear second-order differential equation, it's actually pretty unlikely that you can even write down an explicit solution. And so linear second-order differential equations are going to be easier to solve, but still extremely rich and interesting. So let me just tell you what it means for a second-order differential equation to be linear. And this is actually going to be very similar to the definition I wrote down for a first-order differential equation to be linear. So second-order differential equation is called linear if it has the following form. So if it has the form, okay, so we're going to have a second derivative, y double prime. I'll use y as my dependent variable. Plus some function of t, could be any function of t, times y prime, plus some other function of t, perhaps, times y. And that's going to equal yet another function of t. Okay, so that is a linear second-order differential equation. And if f of t is 0, so if the function you get on that side is 0, then we have a special name for that, and it is called homogeneous. So we had this term also for first-order differential equations. Okay, and if not, so otherwise, it is called inhomogeneous. Okay. So before I talk about how to solve these, I want to give you some idea of just where do these come from. So where do these come from? Where do these come from? Okay. And we already actually saw an example. So I'll make that example 1. This is from the very first lecture. It was the mass spring system. That turns out to be a second-order linear differential equation. So draw our picture that we had from before, if I remember it. So we had a mass here, so this block, and we were assuming there was no friction or anything like that. And then we have it attached to the wall here by a spring. Okay. And so this is a mass. Let's say the mass is m. And we had maybe an initial position, or not an initial position, sorry, the equilibrium position. So this would be where the block would just sit there and do nothing. So in this situation, it looks like we stretched the spring a bit. And then the position of the block, well, that was the function we wanted to study. So let's call that x of t. Okay. So if you recall, how do we get the differential equation? Well, the way we got it was we used Hooke's law. So Hooke's law was the relevant physical law. And do you remember what Hooke's law said? It said that the force due to the spring, well, it's actually proportional to the displacement. And it acts in the opposite direction, so I need a negative sign there. All right, so if the block stretches the spring out, then the spring will want to actually pull it back. Okay, so that's Hooke's law. And then Newton's law, Newton's second law, allowed us to write m times a. A is actually just the second derivative of position, right? So d, the second derivative of x with respect to t, that equals negative kx. Okay. And let me actually move everything to one side. So I have m times the second derivative plus k times x. That's going to equal 0. So what do we have here? What we have here is a linear second order. And is it homogeneous or inhomogeneous? This one is homogeneous because when we write it in this form, we just get 0 on that side. So it's linear second order homogeneous. Okay. And I want to give you a quick problem. So here's a problem. So first I'm going to set omega equal to the square root of k over m. So that's a special number for this differential equation. So if omega, oh, I need a square there. If omega is the square root of k over m, what I'd like you to try is show that all the following are possible solutions to this differential equation. So here's one, sine omega t. Here's another one. So x of t could be actually a cosine of omega t. X of t could actually just be 0. That one we can just show right now, because if we plug in 0, its second derivative is also 0, so we just get 0 equals 0. So we can actually check that one off. X equals 0. And here's a more interesting one, but this is also a solution. You should really check this. So what do I mean by check it? I mean is, take its second derivative and then plug it in. Plug in the second derivative there and plug in the function itself there. And remember that omega is this number here. So this one is 3 times sine omega t plus 4 times cosine omega t. That turns out to be a solution. So check that these are solutions to the differential equation. Okay. So that's your first task, and then your second task is then find 3 more, or at least 3 more. So if you kind of look at what I'm doing with this one, then you should get the idea. So you can try plugging that in and see why it is a solution, and then you'll see the idea. Okay. I'd like to do another example now. This is actually just going to be the same example with a twist. So this will be the mass spring system with damping. Okay. So just going to draw another picture really quick. Okay, so I'm going to add something here. So maybe there's like a piston here. Okay, and then I have the spring. And then finally over here I have my mass. Okay, add a little color to this. Okay, so this is my mass. And this thing right here is called a dashpot. And again, we have an equilibrium position maybe. We want to study the position of the mass. So what does the dashpot do? The dashpot it exerts a force that's proportional, so not to the position, but to the velocity of the object. That's proportional to the velocity. So we'll call that v of t. And in the opposite direction again. Yeah, so this is velocity. So if I'm moving very quickly, this is going to exert a larger force, and it will try to be counteracting that velocity. You've probably seen these dashpots, so these are often installed at the top of a door to basically keep it from slamming shut. And you can try an experiment for yourself. Like if you push the door harder, it will actually try to resist your motion more. So if you try to push it faster, it will actually try to resist you more. And so that's what the dashpot does. It exerts a force proportional to velocity in the opposite direction. So let's modify our differential equation. So now we actually have two forces. So we need to write the net force is, well, it's the force due to the spring, negative kx. But then I also have the force due to the dashpot. That is proportional to the velocity. So I'll call it gamma times the velocity. Well, what is the velocity? Dx dt. So this gamma is called the damping coefficient. Damping coefficient. It damps the motion. I think we talked about this before, but that k is called the spring constant. So let's mention that again. So we have a spring constant, we have a damping coefficient. Let's again use Newton's second law. So we have m times the second derivative of position is negative kx minus gamma times dx dt. And if we go on to the next page, and let's move everything over to the same side. So we have m times, I'm going to try to use the more physics notation. So I'll call the second derivative of x with respect to position x double dot. This is Newton's original notation for a derivative, and physicists or mathematical physicists will often use this to indicate a time derivative. So this is a derivative of x with respect to time. It's just a lot easier to write this than to have to write this whole thing. So m times x double dot plus gamma times x single dot, right, single derivative with respect to time, plus kx equals 0. That's our differential equation. And this is again, this is linear, second order, and it's homogeneous. So you have 0. Great. So that's our first example. We'll talk about how to solve this in great detail, but for now I just want to give the differential equation. Our second example, I'll try to go through this one quickly. This is the Rlc series circuit. So we saw the RC series circuit before. What is the Rlc series circuit? Let me just draw what that looks like. So we have a voltage source here, just like before. And maybe we have one of these switches again. So it looks like this. And then I'm just going to leave some space here to draw in the components. Actually going to have 3 components here other than the voltage source. So we're going to have a resistor and we're going to have a capacitor. So we're already familiar with these two from the lecture on RC circuits. And then we're going to have a third component here. It's called a coil or an inductor. Let me draw on the switch also. Yeah, so this one right here is an inductor. And it has an inductance. That's its associated constant. An inductance L. And the unit is called the Henry. And, okay, so there's our Rlc series circuit. And what is the relevant physical law here? We talked about this before. It's Kirchhoff's law. Kirchhoff's second law in particular, which says the sum of voltages in a closed loop is 0. Okay, so if you go around a closed loop, add up all the voltages, you'll get 0. And so let's go ahead and do this. So I'm just going to do this quickly because for these three, I'm just repeating what I had in a previous video. So here's my voltage across the resistor. It's IR, but with a minus sign because the voltage is dropping. And then my voltage across the capacitor is Q over C, but again with a minus sign. Now I have to tell you something new. So what is the voltage across the inductor? So voltage across the inductor is actually this inductance L times the derivative of the current. Okay. So let's write that in. And again, this has a negative sign because the voltage is dropping by this much. And then finally, we have our voltage source, which I'm just going to call the voltage Vt. And the voltage is increasing by V of t. So assuming that this switch is here, and we have this full loop here, then I get this equation, and this all equals 0. Now, let's also recall, looks like we have too many variables here. I mean, R, L, and C are all constants, but this I here represents the current, and this Q here represents the charge. Both of those are functions of t. Q of t or I of t, either of those we would like to study. But let's just recall they're actually related to each other. I is actually the derivative of the charge. So I is dq dt with respect to time. Which means my differential equation is the following. So I'm just going to move all these ones with the minus sign over. So I get L times, what is this? This is Q double prime, right? Because I is already the derivative, and this is a second derivative of charge. Plus R times Q, that's that term, plus 1 over C, times Q prime, because it's I is the derivative of Q, plus 1 over C times Q, and that's going to equal V of t. Okay. At least when the switch is open, it could also equal 0 if the switch is closed. In fact, yeah, this one corresponds to an inhomogeneous differential equation. And this one corresponds to a homogeneous differential equation, depending on whether we're applying a voltage or not. And this is also linear. And there's something striking here. So I'd just like to point this out now. This differential equation and this differential equation are exactly the same except for these constants. Right? Here we have L, R, and 1 over C. Here we have M, gamma, and K. But that actually, like before we even try to solve these differential equations, this tells us there's actually a deep connection between this problem of the circuit, the RLC circuit, and this problem of the mass spring with damping. They're actually just the same problem mathematically. So in other words, like even if you're having a hard time imagining, well, what is the charge, or what are these things doing, you can actually think of this charge function as the position function of a mass attached to a spring with some damping coefficient. So that's a really useful observation to make at the moment. Okay, so I've done enough examples. I'd like to actually talk about the solutions to these linear homogeneous equations. So solutions to linear, let's stick with homogeneous equations for now. We'll talk about both homogeneous and inhomogeneous differential equations. How do solutions to a homogeneous linear equation work? And I foreshadowed this in the lecture about RC circuits. And so there are actually two important statements, or facts, theorems. Let's call it fact. So fact one. Okay, so here's the first very important fact about linear homogeneous equations. So if y1 of t and y2 of t are solutions to a homogeneous linear differential equation. Here I'm putting a second order differential equation because that's what we're going to be studying. But this actually works. You can basically use the same argument for any order that you want. You need more solutions, but yeah. So let's say these are solutions to this differential equation. Then C1, some constant, times the first one, times the first solution, plus C2, possibly different constant, times the second one. This is also a solution. This is for any C1 and a C2. Okay, so solutions to linear homogeneous equations have this very nice property. If you have two of them, you can get more by just multiplying them by constants and adding them. Let's see why this is true. So, okay, so we're going to assume, let's assume that we have, so y1, I'll just write y1 and y2. So let's assume these are solutions. And then we're going to let y of t be this thing. And we'll pick two constants, C1 and C2. Okay. Well, we want to see why this is true. So what are we trying to do? We're trying to prove that this is actually going to be a solution as well, right? We're just assuming that these two are individually solutions. We're not already assuming that this one is a solution. So we're just defining y of t to be that. And now we're going to check to see if this is a solution by plugging it into the differential equation. So let's do that. So I'm going to plug this in for y. Okay, so let me write out the differential equation. I'll write it from this side. So q of t times this thing, c1 y1 plus c2 y2 equals 0. And then what do I have to put for y prime? Well, I know how to take the derivative of that, right? It's just a sum, and these are constants. So the derivative is just c1 y1 prime plus c2 y2 prime. Notice that we're really using the linearity here of the derivative, Right? The derivative distributes over sums. And you can pull out constants. So this is P of t. And then y double prime, what is that? That's C1 y1 double prime plus C2 y2 double prime. Okay? So I'm just plugging this in. Now I'm going to rearrange it. So I'm going to write this as C1. I'm just going to take all the terms that have a C1. I'll factor that out, in fact. So let's write those terms. I1 prime plus q of t times y1. And then we have plus c2, and then I'll factor that. Plus p of t times y2 prime plus q of t times y2. And okay, so I actually don't know if that equals 0 yet. This is what I want to show. I want to show that this is a solution. All right, so that's why I'm plugging it in. I want to show that I actually get 0. But if you stare at this, you'll realize that we do, because what is this right here? This is my original differential equation with, it's the left side at least, with y1 plugged in. But y1 is a solution, which means this, when I plug in y1, I get 0. That's what it means to be a solution to this differential equation. So this actually equals 0. And similarly for this one, right? This is just the original, this left side of the differential equation with y2 plugged in. So that equals 0. So I get 0 plus 0 equals 0. That's true. So we just proved that this, no matter what C1 and C2 are, doesn't matter. We proved that this is going to also be a solution, as long as we started with 2 solutions. So that's why fact 1 is true. So again, in words, what we're saying is all we need is 2 solutions, and then we can just generate infinitely many more. And notice we have actually 2 degrees of freedom here. We have 2 arbitrary constants. Okay, what is the second fact? So this one I'm actually not going to prove because it's quite a bit trickier to prove, but we're definitely going to need to use it. So you definitely want to understand the statement. Okay, so let's now say I have so if y1, so it's going to start similarly. y1 and y2 are solutions to this same differential equation. So let's just emphasize that it has to be homogeneous and it has to be linear, right? We're using both of those facts here. We use both of those facts in this argument here. Okay, so if there's solutions to this differential equation, then this is really amazing. So then all solutions to the differential equation, I can tell you what they all look like. All solutions have the form. Yeah, so it's pretty crazy. So they have the form C1 y1 plus C2 y2, where y1 and y2 are just those 2 that you happen to start with. And this isn't always true, but this is true if, so all solutions have the form if y1 and y2 are linearly independent. Okay. What does linearly independent mean? It just means one is not a constant multiple of the other in this case. Okay. So as long as we have our hands on 2 solutions, where one's just not a constant multiple of the other, so they're they're different looking solutions, then we actually can write down every single solution to this linear differential equation. They all have this form. So in other words, this is the general solution. This is the general solution to the second order linear differential equation. It's all the solutions. Okay, so technically I'm being a little bit inaccurate about something. So it's linearly independent. Okay, so there's technically different conditions. So let me just say that. So technically, linearly independent. That's actually not quite enough. So it should be replaced with a weirder looking condition. So it should be replaced by y1 of t times the derivative of y2 of t minus y2 of t times the derivative of y1 of t. That has to be the zero function. Okay? So if y1 and y2 satisfy this relationship, then all solutions have this form. This is called the Wronskian determinant. Wronskian. We're actually just going to use this condition, linearly independent, because it's easier to check. It's easier to see if one is not not a constant multiple of the other. And for all the examples we're going to be doing, these are basically equivalent. But yes, technically I should replace linearly independent with this condition. Okay, so I think we've talked enough about where these come from, a little bit of the theory behind them. Let's actually try to solve some linear second order equations. Okay, so this is the fun part. Okay, and actually, what I plan to do for the next several lectures, I'd just like to focus on an even smaller class of linear homogeneous equations. These will be linearly homogeneous equations with constant coefficients. So those are going to look like this. Y double prime plus, I had P of t here before. I'm just going to put A. So AY prime plus BY equals 0 because it's homogeneous. So we're just going to focus on ones that look like this for now. And you might think, well, that's way too restrictive. Like, why are we just doing that? But now if we look back at the mass spring equation, M, gamma, and K are constants, right? We didn't have functions of t appear here. And same with the Rlc circuit. They're just constant coefficients here. So there's certainly a lot of very interesting behavior you can get with just these kind of differential equations. And they come up a lot in practice. So here's how you solve them. So let's call this the solution idea. So this is the idea behind how to solve them. And we're going to try this, and we're going to see it runs into some problems. But there's a good idea, and the idea is to guess. Okay, so that does not seem so satisfying, but we're going to make an educated guess for the solution. So the solution is going to be y of t equals something. That something, I'd like to start by guessing an exponential, e to the rt, let's say. Or r is just some number that we don't know. We don't know yet, but we will be able to figure out what r is. Okay, well, why am I guessing an exponential? Here's why. So let's take the derivatives. We have r e to the rt, r squared e to the rt. Look what happens when we plug it in. We get r squared e to the rt plus a r e to the rt plus b e to the rt equals 0, if it is truly a solution. We don't know if this is even going to work, but look at what happens, right? We have an e to the RT, each term, that's never 0, so we can divide by it. So we get r squared plus ar plus b equals 0. That's just a quadratic equation. And so this quadratic equation, so first of all, yeah, this has a name. This is called a characteristic polynomial, or characteristic equation. Characteristic polynomial. And so the reason for this guess is now very clear. If we can just solve this quadratic, we get two values of r, and those will correspond to two solutions. Well, you might say we only have two solutions. How do we get the general solution? That's where this comes in, all right? This fact 2. So if we have two solutions, as long as they're different, as long as they're linearly independent, so if one is like e to the 2t and the other is e to the 3t, we're good, right? Because one of them is not a constant multiple of the other. Then we can just write down the general solution. It's just this right here, right? Where y1 is the first solution, y2 is the second solution. Okay, so you might have noticed there are a few difficulties with this. First of all, not every quadratic has two real roots. In fact, yeah, so there are three possibilities for the roots of a quadratic. Three possibilities. First possibility, two real roots. That's what we're going to talk about today. Second possibility, two complex roots. And the third possibility is sometimes a quadratic only has one real root, but it's repeated. So one repeated real root. It turns out you cannot have one repeated non-real root, one repeated complex root. That's not possible. So if you have a double root, it has to be real. So those are the only three possibilities. And so let's look at the first possibility. So case 1, if there are two real roots, well, let's give them names. So let's say there R1 and R2 are real roots to this characteristic polynomial here that we get. They correspond to solutions to the differential equation. They correspond to solutions. Let's cross it out. To the differential equation. What are those solutions? Well, what was our guess? It was e to the RT. So the solutions are y1 is going to be e to the r1t. y2 will be e to the r2t. And so the general solution, we can just write it down right now using our facts from the previous page. General solution is going to be y of t is c1 times the first one, e to the r1t, plus c2 times the second one. So by the first fact, anything of this form has to be a solution. That's what we proved. And then by the second fact, every solution to this differential equation must be exactly of this form. We must be able to write it in this form. Okay, so we'll do an example of this. But I just want to point out, so what are we going to do in these cases? It's not so clear because, well, what if we had two complex roots? Then again, we have e to the r1t, e to the r2t, but those r1 and r2 are complex, so we actually get complex solutions. We get complex functions. And in a lot of these applications that we're interested in, we don't want complex solutions. We want real solutions. So that's going to be the difficulty for that case. How do you turn these complex solutions into real solutions? Can you think of what the difficulty will be in this third case? What if we just have one real root? Well then great, e to the, let's call it r, right? So e to the RT will be a solution to the differential equation. But it's only one solution. Remember, we need two different solutions in order to form our general solution. We need two linearly independent solutions also. So we can't just multiply this one by a constant. That won't be linearly independent. So that's going to be the difficulty in that case. Okay, so we clearly have some work to do for these cases 2 and 3, but let's actually try to solve a differential equation where we get case 1, just to show that it's actually not too bad. So let's solve, in fact, let's do an initial value problem. So solve the initial value problem. Y double prime plus, I'm going to write down a particular differential equation, 5y prime plus 6y equals 0. And here are my initial conditions. I said conditions plural because I actually need to give you two of them. Why is that? Because there are two arbitrary constants that we're going to need to pin down. Right? So how am I going to give you two of them? Often in practice, the way this is done is you give what y of 0 is, and you also give what y prime of 0 is. So y of 0 is going to be 2, y prime of 0, that'll be 3. So these are my initial conditions. Okay, so what do? Well, we just follow the same idea. So we guess e to the RT. E to the RT. That's our guess for a solution. And we need two of them. Okay, so e to the RT, what happened when we plugged it into the differential equation? We ended up with this equation, the characteristic polynomial. Okay. So what was our characteristic polynomial? Is let me write that. R squared plus AR plus B, so it would be R squared plus 5R plus 6 equals 0. Okay. This quadratic we can factor, so it's R plus 2, R plus 3 equals 0. So what are my roots? My roots are 2 and -2 and -3. Sorry. Those correspond to solutions e to the -2t and e to the -3t. And e to the -2t, so let me just write this down. So here are two solutions, e to the -2t and e to the -3t. And what can we say about these solutions? These are linearly independent. One of these is not just a constant multiple of the other. If you do this one divided by that one, you don't get a constant. Okay? So we can immediately write down our general solution. It's C1. I have to use C1 and C2 just because I have to index these two constants. C1 e to the -2t plus C2 e to the -3t. I should say y equals. Right? So that's my general solution. Okay, we're almost done. We just need to now plug in our initial conditions. Okay, so what if we use the first one? Plug in 0 for t and 2 for y, so we just get 2 equals C1 plus C2. How do I plug in the second one? Well, that's not too bad. You just we have what y equals. We can actually take the derivative of y, so it's just taking a derivative. So y prime is going to equal -2c1 e to the -2t minus 3c2 e to the -2t. Right? And then we can plug in the second initial condition. And right, because we can't really get any further with this, so let's plug in the second one, and we get 3 equals negative 2c1, let's plug in 0 for t, minus 3c2. And what do we have here? We have a system of 2 equations that we can now solve for c1 and c2. So often in these problems you have to solve a system of equations as part of the solution, but we can do that. So how do we solve this system of equations? This is a system of equations. Well, there are many ways. Maybe what I'll do is, so if I want c1, I want to eliminate c2, so I'll multiply this first equation, this one here, by 3. So we get 6 equals 3c1 plus 3c2, and then this one I'll just leave as is, minus 2c1 minus 3c2. See, that way I can just add them, and then these terms go away. So we get 9 equals c1. I just add these two, which means that c2, what does that have to be? Well, 9 plus c2 is 2, so c2 is negative 7. Great. So what is my solution to the initial value problem? It's c1, which is 9 e to the negative 2t, minus 7 e to the negative 3t. And I'm done. So we solved our first second-order linear differential equation. So next time we're going to talk about what to do in this case. What if we have complex roots for the characteristic polynomial?